Alright, hey there guys. My name is Wilfrid, and I'm a senior math tutor, and today I'll be covering 13 questions, ranging from algebra to functions to calculus and vectors here. A little bit backstory upon myself. I recently graduated from McMaster with a major in biochemistry and minor in mathematics. And yeah, I'll just be going through these questions with you guys today. If you guys have any other questions with your homework or with your tests or with any other, if you have any other confusions, just please submit them through OneClass and we'll try to get to them as soon as possible. Alright, so let's just jump right into it. Alright, so the first question reads, how do you evaluate log of base 3 of 27? So the logarithmic function, it basically outputs the exponent that will be that correlates to a power and an argument. So for example, let's say that we have 10 to the power of 2. Okay, so we know 10 to the power of 2 is equal to 100. So another way to I guess write this is to use the logarithmic function. So we have a log of base 10. So the base is 10, so we put the 10 here. And we put the argument or the output of this exponent into here, and it will output the exponent that will make 100 from base 10. Okay, so the general form of this is as follows. So we have a base of, I guess, b to the power of a equals x. Then the logarithmic function would be log of base b x equals the exponent a. Okay, so now let's try to evaluate log of base 3. So we're no longer in terms of base 10, we're in base 3s now. So we're going to evaluate log of base 3 of 27. So this is basically asking us how many 3's fit within 27. So how many 3's multiplied together equals 27. Okay, so let's try to think of this in two ways. So the junior tutor, they used a bunch of logarithmic rules to find the answer, but we're just going to try to do this through computation. Okay, so how many 3's fit into 27? Okay, so let's see here. So we have 27 here. So if we were to divide this by 3, we would get 9. Sorry, we'll get 9. Okay, so if we were to divide it by 3, we would get 9. Right? So if we were to divide it by 3 again, we would get 3. Alright? And if we were to divide it by 3 again, we get 1. Alright? So how many 3's multiplied together equal 27? We got 3 3's. So the log of base 3 of 27 is 3. Okay? So the junior tutor used logarithmic rules to calculate this. So we're going to just go through that too, okay? So the first logarithmic rule is the logarithmic rule of powers, which suggests that we can write the log of base a of x to the power of b as b times log, let me just get out of here, b times log of a, well, log base of a of x. Okay, so this is what the power will suggest. If we have an argument which has a power in it, we can take that exponent and move it outside and multiply it to our logarithmic expression here. Okay, so the second rule that they use is this. Okay, so log of base b with argument b is equal to 1. Okay, so they use these two logarithmic rules to calculate the log of base 3 of 27. Okay, so first of all, let's use our power rule. All right, so this is the first way, and we'll do the second way right now. Okay, so so we have log of base 3 of 27 equals what? Okay, so first of all, we have the log of base 3 of 27 can also be written as the log of base 3 of 3 to the power of 3. Okay? So according to our power rule, we can move this exponent out and multiply it to our whole logarithmic expression, and we get log of base 3 of 3. We're going to use our second rule, which suggests that the log of base b of b is equal to 1. So all we get is 3 times 1, and we get 3. Okay, so those are two ways to think about calculating log of base logs by using a computational method and also using some properties of logarithms themselves. Okay, so the junior tutor, they use the properties of logarithms to simplify our expression and find the answer to our expression. Okay, so the solution is correct. Good work. All right. Cool. All right, let's move on to the second question here. So the second question reads, what is 1 plus x cubed? And I'm assuming that they're asking us to expand it out into all its terms, okay? All right, so I've previously talked about FOIL method before, and I'll explain it again. So let's first of all, let's write 1 plus x cubed first. So I'm just going to rewrite it like this. This is the same thing. So 1 plus 1, x plus 1 cubed is also equal to x plus 1 times x plus 1 times x plus 1, okay? So we're going to FOIL our first two brackets, or our first two terms. We're going to FOIL these two brackets, okay? And we FOIL those together. What does FOIL stand for? FOIL stands for the multiplication of the first outside, inside, and last terms, okay? And once we multiply each of these steps, we add them all together, okay? So if we FOIL, what we're going to get? So x times x, the first terms, right? That's x squared. All right, so the outside terms, so if you think about this like I guess in a more spatial sense, the outside terms are the two outward terms. So x times 1 is x, so plus x. The inside terms are the ones on the inside, so 1 times x is x. And the last terms of each bracket is 1 times 1 is 1, okay? So we get this huge big bracket. We're going to simplify this now, so x squared plus 2x plus 1 times x plus 1. So we still have not fully expanded this because we still have this term. So we're going to use our FOIL method, but the FOIL method only can only be, I guess, correctly applied to these two terms, because in this scenario here, we have 3 terms and 2 terms here. So we can't really label one as an inside term and one as outside, okay? So the general principle of the FOIL method is that you want to multiply all of these terms with all the other elements of the other term. Okay, so you want to multiply x squared by x and by 1, okay? So you want to multiply this by this and this by this, okay? You also want to multiply 2x by x here and by 1 here, okay? And finally, you want to multiply the last one, so you want to multiply 1 times x and 1 times 1, and you would add them all these products together, okay? So let's do that. So x squared plus times x is x cubed. X squared times 1 is x squared. 2x times x is 2x squared. 2x times 1 is 2x. 1 times x is x. And 1 times 1 is 1, okay? So now we're going to simplify this all together, and we get x cubed plus 3x squared plus 3x plus 1. Okay, so that is how you expand these terms, okay? So the junior tutor also posted the FOIL method, and then after they distributed all the terms together and added them together, they had to multiply this 3-term bracket by this 2-term bracket. So use the distributive property again and added it all together and simplified to get our answer. So this solution is correct. Nice stuff. Cool. All right. Let's talk about the next question here. All right. So what is the discriminant of the quadratic equation 4x squared minus 2x plus 1 equals 0? So the discriminant is based off the quadratic formula, and the quadratic formula goes like this. So the quadratic formula is applied to second-degree polynomials. It helps us to solve for the solutions to this equation here. So it solves for values of x, which will make this equation true. So it uses the coefficients of our quadratic equation, and so the values of x will be equal to minus b plus or minus b squared minus 4ac divided by 2a. Okay, so the discriminant is based off this quadratic formula, and the discriminant can help us to determine how many solutions to this equation do we have. Do we have no solutions? Do we have one solution, or do we have two solutions? Okay, so this discriminant is based off this part of the formula right here, which is b squared minus 4a. Oh, whoops. Okay, so we're going to say discriminant d is equal to b squared minus 4a c. All right, and the properties of d will help us to determine how many solutions to this equation. How many solutions are to the equation? Okay, so if d is greater than 0, we have two solutions. Okay, if d is equal to 0, we have one solution. And if d is less than 0, we have 0 solutions. Okay, so let us apply our learning here to our example. Okay, so we have our quadratic equation 4x squared minus 2x plus 1, right? So 4x squared minus 2x plus 1. And what are our coefficients here? Our coefficients are, our 4 is the a, our negative 2 is the b, and our 1 is the c. Okay, so applying our discriminant formula here, we have this. So d equals b squared minus 4ac, which will equal to negative 2 squared minus 4 times 1. Okay, and this is what we get. We get 4 minus 16, so we get negative 12. And therefore, we write, since d is less than 0, there are no real solutions. So the reason why I write there are no real solutions is because there may still be complex solutions that solve this equation, but typically, especially in high school math, we don't really cover complex numbers, so we just wrap it up and say that there are no real solutions. Okay, and real means that it's part of the real number line. Okay, cool. So this solution is correct. So the junior tutor, they posted the quadratic formula, and they told us that where the discriminant is based off of. Then they figured out the coefficients of our equation, and they plugged it into our discriminant, and they evaluated whether the discriminant was less than 0, greater than 0, or equal to 0. And since it's less than 0, then we know that the given equation has no real solution. So this is good work, and we can move on. Okay, cool. Let's move on to question number 4. All right, so how do you find the x-intercepts of a quadratic function? So we kind of just covered this in our last question, where the quadratic formula helps us to find the values of x that solve this equation. So our equation here is ax plus bx plus c. So our quadratic formula helps us to solve this equation. It gives us the values of x which will satisfy this equation. Okay. There are other ways to find the x-intercept. For example, you can factor it, and by factoring it, you can find the zeros of our equation. So that's another way that we can find the x-intercepts. Okay. But the x-intercepts are basically the parts of the graph. So let's say that we have, let's say f of x equals to x squared. Okay. So if we were to graph this, it would be it would look like this, right? So our zeros are the parts of our graph where the point it touches the x-axis. So we only have one 0 here, which is in fact 0, 0. Okay. So that is what it means by we want to find the x-intercepts of a quadratic function. So there are two ways of doing this. The first way is to use a quadratic formula. So the first method is quadratic formula. And this is just a lot of computation where you apply the quadratic formula and you find the values of x that solve that equation. So the quadratic formula, like I wrote in the last question, was minus negative b plus or minus b squared minus 4ac divided by 2a. So you plug in your coefficients here, and you solve for this quadratic formula, and you find the values of x. Okay, the second one is called factoring. So basically, I believe there's an example here that we can use. Okay, so there is an example here. So factoring, I'm going to use the example to illustrate. All right, so let's say that our equation is x squared minus 3x plus 2 equals 0. Okay, so we need to find the values of x that satisfy this equation. Well, we can factor this. So it'll be x minus 1 times x minus 2 equals 0. And by factoring it, we can find the values of x that will make this equation to 0. Because we have one term here and another term here. So all we really need to solve is when x minus 1 equals 0. And that's one of the solutions. And when x minus 2 equals 0. Which in fact, x equals 2 and 1. So these are the x-intercepts of our quadratic function, right? Okay. So those are the two possible methods of finding it. I guess the third method is that you can graph the function itself and visually locate our x-intercepts. So that's the third method. And another disclaimer, the last disclaimer that I'm going to post here, is the fact that that for the x-intercepts of a quadratic function, they can either have no x-intercepts. So let's say they can have 0 x-intercepts. So let's say that we have an equation up here, like y equals x squared plus 4. Right? So there is no point on this quadratic function that touches the x-axis. Or we could have another quadratic function that's maybe facing downwards or even upwards, like this, which have 2 x-intercepts, okay? So that is the maximum amount of x-intercepts that a quadratic function can have, okay? So I believe that I covered everything surrounding the x-intercepts of a quadratic function. I guess the last disclaimer is that the x-intercepts can be also equivalent to saying finding the solutions of our quadratic equation or finding the zeros. So whenever they ask you to find the zeros or the solution, they're also asking you to find the x-intercept. Okay. So the junior tutor, they briefly describe what an x-intercept is, and then they posted a example for us to use to find the x-intercept. And they actually used some grouping to find our factors instead of actually just factoring it. But they found our x-intercepts, which is 2, 0, and 1, 0. So this description is good. Nice work. Cool. All right, let's move on to question number 5. Let me just get some water. Okay, so question number 5 reads, how do you find a polynomial function that has zeros, 0, -2, and -3? Okay, so we just covered what a 0 is. A 0 is basically x-intercepts, or the solutions that make an equation equal to 0. Okay, so a polynomial function has this general form. So let's say a polynomial function, let's say p of x, okay? So this is a single variable, has a coefficient, an x to the power of n, plus a coefficient b, x power n minus 1, plus coefficient c, x to the power of n minus 2, plus ... plus coefficient d with x to the power of 0. Okay, so this is what a polynomial function is, right? And a lot of polynomial functions have zeros or x-intercepts. Okay, so basically what this question gave us was that they gave us the zeros at x-intercept, and they asked us to find the polynomial function that corresponds to these zeros. Okay, before I continue, I just want to give you an example. So let's say that P3 has degree 3, so it'll be ax cubed plus bx squared plus cx plus d. Okay, so this is an example of a third degree polynomial function. Okay, all right, so in our previous example, we said that to find the zeros of a quadratic equation, we can either use a quadratic formula, we can use factoring, or we can also visually graph it and find it by locating the zeros on the graph. Okay, so only one solution is really possible here, and that's basically we're going to reverse factor. Okay, What I mean by reverse factor is that we're going to look at each of these zeros and find a factor that corresponds to it equal to 0, okay? So let's say, for example, what value, okay, so let's look at the first 0, okay? So the first 0 is just 0, okay? So what value of, or what factor will correspond to an x equals 0? Well, that means x equals 0, right? So when x equals 0, the equation equals 0. So that means that one of our factors is just x, okay? All right. So therefore, one factor is just x. Okay, what about our 0 of -2? So that means x equals -2, then our formula equals to 0. So p of whatever equals to 0. Okay, so therefore, a factor that is possible for this is x plus 2, right? Because if you think about it, x plus 2 equals 0. So what makes this equation equal to 0 when x equals -2? Okay, so a factor is x plus 2. Let's apply this thinking to our third 0 here. So -3, x equals -3, then a factor is x plus 3. Because what makes this equation equal to 0? X equals -3. Okay, so we have found our factors, which is x, x plus 2, and x plus 3. Okay, so if you combine these all together, we get, so if we're going to multiply all these together, we're getting x times x plus 2 times x plus 3. Okay, let's check our zeros here. Okay, so this is our factored polynomial. Let's check our factors here. So when x equals 0, this whole thing equals 0. Okay, when x equals -2, this bracket here equals to 0, and anything multiplied by 0 is 0. When x equals -3, this bracket equals 0, and everything multiplied by this is equal to 0. So we have found our polynomial, f of x. So let's expand this now, okay? So if we expand, we get f of x equals x squared plus 2x plus times x plus 3. And this gives us x cubed plus 3x squared, so 5x squared plus 6x. Okay? So we use our FOIL method here, first, outside, inside, last, to expand this, and this is our given polynomial. So we have a third degree polynomial with coefficients a, b, and c. There's no d coefficient here. And we also notice that it's a polynomial. So this is the polynomial that corresponds to our zeros of 0, -2, and -3. Okay? So the junior tutor also used that line of thinking. So they found out that the zeros correspond to a factors of these. So they noticed that there's 3 zeros. So that means there has to be 3 factors that correspond to these zeros. Okay? So then they plugged in their zeros here, and they figured out that their factors are x, x plus 2, and x plus 3. They expanded it all together, and they finally got x cubed plus 5x squared plus xx, which is the solution is correct. Good work. Cool. Let's move on to the next question here. Question number 6. Alright, so how do you find the domain and range of a function? Okay. So let me explain to you what a function does again. So a function basically maps one value to another. Okay, so if we were to say that we have a bunch of x's here, okay? So we have a bunch of x's here. So let's say x. And we have a bunch of y's here, okay? So there is a function that will bring us from our x to a y. And we call this f of x, okay? So the domain of a function, right? The domain is all possible values, or all possible input values that are that make f of x defined, or that map to a y function. Okay, so we can say that this is our domain. Any value of x, or any input value of our function that makes our function defined. Okay, so anything that makes it undefined is not part of the domain. Okay, and the range suggests and explains and encapsulate all the possible values of our function f of x. Okay, So everything that the domain maps to is our range. And we can use, just for a note, we can use the f of inverse to take our range and map it back to the domain. Okay? All right, so the question is asking us, how do you find the domain and range of y equals x squared? Okay, so if we write out y equals x squared here, so our domain needs to be all possible values that will make our function defined. And that value is actually all the real numbers. Okay, so our domain D is x belongs to all real values. Okay. All right. Cool. So to find our range, we can use the inverse. We can use the inverse function to find the domain of our inverse function. And we know that the domain of our inverse function is equal to our range. Okay. So if we were to have a, let me make this arrow a different color here. So let's say that our inverse function is in green here. So our inverse function, and that's written out by f of inverse 1 of x, takes our domain, which is our y, and brings it back to a range. Okay, so we can find our range of our function here, y equals x squared, by finding the inverse. Okay, so if we find the inverse, that means that we're going to solve for x, and our inverse is x equals root of y. Okay, so now we're going to solve it for the domain of this, right? So the nature of square roots is that it can only square root positive numbers. So our domain here, I'm going to write it in green, is y is greater or equal to 0. Okay, and also y belongs to the real numbers. Okay, so this is our domain of our inverse function. Okay, our inverse function suggests that the domain, because of the nature of a square root, that the number within the square root has to be positive. So that means that y has to be greater or equal to 0, and y is all the real numbers. So actually our range is y is greater or equal to 0. Okay. So another way you can find the domain and range of our function is by graphing them out and visually looking at our graph and saying, what are the possible values of x in terms of the domain that makes this function undefined? And in terms of the range, what are the possible values of y that exist on this function? Okay, so that's another way to think about it. And so the Junior Tutor, they use these brackets instead of these curly brackets. So I'm going to write it in that sense too. So the domain of our function here is from negative infinity to positive infinity, right? Because that's all the real numbers. And our range here is from 0 to infinity. And we need to put a closed bracket here because it includes 0. Okay, so this is our domain and range of y equals x squared. So this solution is correct. Good work. Cool. All right, question number 7. All right, so the question reads, how do you solve 4x squared minus 64 equals 0 using quadratic formula? So I've stated the quadratic formula in the past, but I'm just going to write it again so we can reference it easier. All right, so our quadratic formula based on quadratic equation ax squared plus bx plus c equals 0 is equal to the values of x, that minus b plus or minus b squared minus 4ac divided by 2a. Okay, so we're going to use this quadratic formula to solve our quadratic equation. So we have 4x squared minus 64 equal to 0. We recognize that we don't have a b coefficient, but we have an a and a c here. So we're just going to plug that into our equation here. So we have no b, so x equals 0 plus or minus 0 squared minus 4 times negative 64 okay, divided by 16. Or 8, sorry. Okay, so if we were to simplify this, we have plus or minus 16 times 64. It's root of 1024. Okay, divided by 8. Okay, so now we need to split this up into a plus or minus situation here. So the root of 1024 is just 32. So we have plus or minus 32 divided by 8. So our zeros here are -4 and 4. Alright, so that's how you solve for the zeros, or the solutions to our quadratic equation for x squared minus 64. And just one thing to note, so I said previously that there are 3 techniques. You can use a quadratic formula, you can factor, or you can graph it, right? So the quadratic formula, in my case, and in a lot of cases, I really like to apply the quadratic formula when it's not easily factorable or it's not easily graphable. Okay, so I would expend those solutions first before applying the quadratic formula, because if you use those solutions first, then you probably have a very simple solution. But in the case of a quadratic formula, you usually use it for very complex solutions, not in terms of complex numbers, but stuff that you can't factor, and it's very complicated to solve for. Okay. So the junior tutor, they used the quadratic formula correctly here, and they found our answers. So x equals 4, x equals -4. Make this equation true. If you guys want to check, you guys can check it here, but otherwise the solution is correct. So cool. All right, moving along to question number 8. All right, so we're going to move on to some integration and derivatives. So the question reads, evaluate the indefinite integral, the integral of x squared e times e to the power of x cubed. Okay. So given this integral here, I'm just going to write it out. We're going to use our substitution rules to simplify this integral so that it's easier for us to use. And the substitution rules basically allow us to set a temporary variable to be equal to something within our integral, and then solving and deriving that to find a easier integral. So I'll just show you by example. So if we have integral of x squared times e to the power of x cubed dx. So we're going to let our temporary variable u equal x cubed. Okay, so du dx of x cubed is just 3x squared. And if we were to treat these as separate variables, then we get dx equals dx equals du hold on, let me write this differently actually. Du over dx, so dx 3x squared, or just x squared, x squared dx equals du over 3. Okay? So du over 3 equals x squared dx. Okay, so we're going to label this to be 1 and label this to be 2. Okay, so we're going to sub 1 and 2 into our integral. So sub 1 and 2. So if we sub 1 and 2, this is what we get. Okay, so we know u equals to x cubed, so we're going to write e to the power of u. And we have x squared dx, which equals to du over 3. Alright, so this is our integral here. So we can factor out any constants here, which is 1 over 3, and we get e to the power of u du. Okay, so we know that integral, or even the derivative of any function with e to the power of something is just e to that power of something again. So we can write this as 1 over 3 times eu. Okay? And we need to remember we have to include a constant here. The constant can be anything, but we just assume that there's always a constant in an indefinite integral. Okay? So now we have 1 over 3 eu plus c, and we're going to sub u back in. and this is what we get. 1 over 3 e to the power of x cubed. Okay, so this is our indefinite integral of this integral. So substitution was a very useful method of simplifying it and making it easily interpretable so that we can solve it. So then again, you guys can already look at this integral and you guys can kind of solve it in your head, but this is a more easier approach to doing that, especially for very complicated integrals that you really cannot just do in your head, right? So there you go. So this solution is correct. Good use of substitution. Cool. All right. We're going to talk about question number 9 now. Okay. So how do you find the instantaneous rate of change of a function at a point? Okay, so the junior tutor wrote that the instantaneous rate of change, or the IROC of a function at a point, can be determined by getting the derivative of a function and then substituting the value of x of the given point to the derived function. Okay, so another way of describing the instantaneous rate of change of a function is finding the slope of a tangent line to that point. Okay, and we need to differentiate between a tangent line and a secant line, so I'll go through that right now. Okay, so let's say that we have our graph here. Let me just zoom out first. Okay, so let's say that we have a graph here, okay? And let's say our function looks like, let's make it a squiggly guy, okay? Let's make it like this, okay? So this is our function, f of x. Okay, so a secant line is a type of line that is the slope between 2 points on the function, okay? So let's say that we want to find the slope between this point and this point. So this line here this line here, if I can draw it correctly. Okay, I didn't draw it correctly, but what can you do about that? Okay, so this line, and we'll say that this is a secant line. The slope of this line is called the average rate of change, or the AROC, okay? And it helps us to see the rate of change between these 2 points. So we see here that the slope is positive, so the average rate of change at these 2 points is a net positive, okay? So we can see here from this point to this point it increases slightly, right? Even though the nature of the graph, it increases and then it decreases, the AROC tells us that from this point to this point, the y value increases slightly. Okay, so how does this compare to our secant line, or tangent line? Okay, so a tangent line is the slope of a line that is just touching one point on the graph. Okay, so this is what we call our tangent line. Okay, and the slope of this line gives us what we call the instantaneous rate of change. Okay. So it helps us to understand the behavior of this graph at this certain point. So if it's positive, that means it's increasing. If it's negative, then it's decreasing. Right? The slope of this line is positive, so we know that it's increasing. By how much? The magnitude of the slope will tell us that. Okay, so finding the tangent line to this point on the graph is equivalent to finding the derivative of the function itself and plugging in the given point, the value of x, into our derivative. And by doing that, we have found the slope of our tangent line at that given point. Okay, so let's use an example that the junior tutor provided us. Okay, so the example that they gave us was f of x equals to x cubed. Okay, so if we want to find the IROC at point 1, 2, we have to first derive this, okay? So we need f prime of x. Now equal to 3x squared. Now all we need to do is to plug in our point here, and we get 3. So we know at point 1, 2 on our graph, we have, is that even a legitimate point on our graph? It's not, but it's okay. It's fine. we know that at point x equals 1, that our instantaneous rate of change is equal to 3. That means that it's positive. That means the function is increasing by a magnitude of 3 units per whatever, okay? So that's how you find the instantaneous rate of change of a function at a point. So this description is correct. Good work. All right. Let's tackle question number 10 next. All right, so would you look at that? We're now going to try to find the equation of the tangent line to the curve e to the power of 2x times cos pi of x at 0 and 1. Okay. So we just explained how to find the equation of, or the slope of the tangent line, which means that we have to derive this function and then plug in x equals 0 into our function, okay? So let's write out this, our function first, which is y equals e to the power of 2x times cos times of pi x. Okay, so y prime is equal to, so this is a product rule and a chain rule. So we're going to derive this and multiply it by this function first. So the derivative of e to the power of 2x is just 2 times e to the 2x times cos pi of x. And since it's a product rule, we'll have to derive this and leave this one alone. So the derivative of cos pi of x is a chain rule, so it's going to be negative pi of sine pi x, all right, times e to the 2x. Okay, so we simplify this, we get e to the 2x of 2 cos pi x minus pi sine pi x, okay? All right, cool. So now we're going to plug in our x value, which is 0. So y prime of 0 is equal to e to the 0 times 2 of cos 0 minus pi of sine 0. Okay, so sorry about that. I forgot my 2 here. Oh, my 2 is here. Okay, so e to the 0 is just 1. Any power of 0 is just equal to 1. Cos of 0 is equal to 1, so it's equal to 2, and this equals to 0, so we get 2. So we now know that the slope of our tangent line is 2. Okay, so now we need to find the equation of our tangent line, so we can plug it into our equation here. So our line equation is y equals mt x plus b. And we know that this line, it has a point at 0, 1. So we're just going to plug this in here. 0 plus b. And we get that b equals to 1. So finally, we have our line equation. Therefore, the equation of the tangent line at 0, 1 of function x equals e to x cos pi of x is, so we're going to plug in our b and our mt, which is equal to mt y equals 2x plus 1. Okay? So this is the equation of our tangent line to the curve. Alright, so the junior tutor also did the solution. They found the slope of the tangent line by finding the derivative of the function at the point x1. They solved for the derivative, they plugged in x equals 0 to find the slope, and then they just subbed it into the line equation and solved for b. So this solution is correct. Good job. Cool. Alright, question number 11. So how do you find the antiderivative of tan squared x? So the antiderivative is another word for indefinite integral. And as the name suggests, you're doing the opposite of a derivative. So you're going back to the opposite way, okay? So the antiderivative of tan squared x is going to be written out like this. And we're going to be using some trigonometric identities to help us simplify this integral and to solve it easier, okay? Alright, so first of all, we know that tan squared x, so we know that tan x is equal to sine over cos x. So we're going to plug that in here. So since we have a square, it's going to be sine squared x over cos squared x d of x. Okay, cool. So the next thing we're going to use is we know that sine squared plus cos squared x is 1. And if we isolate for sine squared x, we get sine squared x equals 1 minus cosine squared x. Okay, so we're going to plug that in there too. So we plug it in here, we get 1 minus cosine squared x over cosine squared x dx, okay? We're going to separate these fractions out. So we're going to have this, so 1 over cosine squared x minus 1 d of x. We're going to use our sum rule for integrals to break up this integral into 1 over cosine squared x, integral of 1 over cosine squared x dx minus the integral of d of x, or 1 of d of x, okay? So another way to write 1 over cosine squared x is secant squared x is equal to 1 over cosine squared x. So we're going to apply that here. So we're going to write secant squared x d of x minus integral of 1 dx. So using the constant rule here, we know that it's equal to x. And using our knowledge of common trigonometric integrals, we know that the integral of secant squared x is just tan x. Alright, so we have here tan x minus x, don't forget the constant, c. So that's the antiderivative of tan squared x. Okay. So the Janine The Tutor also used a bunch of trigonometric identities to simplify our integral here to make it easily solvable. They also applied actually they didn't do that. They did use a difference rule for integrals to separate the integrals, and they used a constant rule to find this integral here. So this solution of tan x minus x plus c is correct. Good work. Okay, cool. So we have 2 more questions. So the next one is kind of a big question, so I'll just try to go through it with you guys right now. So how to use the shell method to find the volume of the solid attained by rotating the region bounded by the curves x equals 4y squared minus y cubed and x equals 0 about the x-axis. Alright, so in previous sessions, I actually solved some of these questions. I think in the last session, I actually used the disk method, so this time we're going to be using the shell method. Okay, so the first thing that you always want to do is you want to figure out the bounds of our integral that you're calculating. Okay, so we want to graph out this function first. So I have x equals 4y squared minus y cubed. Okay, so I'm going to take this function here and graph it out over here. Okay. Alright, so if we have this function here, I'm going to use our same colors too. I'm just going to draw approximate. I'm not going to really draw it out to scale, but it's like here, and then it goes back out like this. Okay, this is what it looks like. So this is actually, so this is the x-axis and this is the y-axis. Okay, so this is the function here. X equals 4y squared minus y cubed. And we also have x equals 0, or the line at the origin here. So this is our line here. So this is x equals 0. Alright, cool. So our bounds for our integral, or our bounds for our solid, is going to be here and here. And in this case, that will be 4 0, 4, and 0, 0. So we know that now the bounds of our region is from 0, 4 to 0, 0. Okay, cool. So now they're telling us that this solid is created by rotating this region around the x-axis. Okay. I think this is actually, hold on, let me go back here first. Okay. So if we're going to rotate it around the x-axis, all right, in this sense, we're going to rotate it this way. Okay, we're rotating it this way. Okay, so we're going to rotate it, and we're going to get like a really weird oval-shaped sphere. Okay. So how are we going to find the volume of this region? Well, the volume of this region, so in previous sessions, I stated the disk and the shell method. Here I'll just state the shell method. Is going to be the integral of the surface area of cylinders within this region. Okay, so pi r h. And there's going to be bounds b of a, and we don't really know what it is, so we'll just write d of let's write d of x right now. Okay, so this is the equation for our volume of the region, and this is basically calculating the surface area of the cylinders that fit within this region and adding them all together. Okay, so let's think about this more geometrically and more in terms of the graph. Okay, so first of all, let's say that let me see if we have a different color here. All right, let's say that we have a rectangle from here to here. All right, let's do more rectangles. So and let's say that we have another rectangle from here to here. Okay, so these rectangles, let's say that for integrals, usually, right, when you're calculating the area under the curve, you're adding together very small intervals of small rectangles, and you're adding all these areas up, and once you add all these areas up, you find the area of this rectangle, right? So when we're applying it to the volume, we're assuming that we're also adding up the area of these rectangles here, right? But also, not only are we adding up the area of these rectangles are also revolving around our x-axis. So this rectangle is revolving around our x-axis, and this one's revolving around our x-axis too. So if you have a rectangle that is revolving around the x-axis, you would kind of see that it makes a cylinder. Okay, so if you guys want to, you guys can pause this video now, and you guys can, I guess, geometrically think about rotating a rectangle around the x-axis like this. Okay, so the rule of thumb between using the disk method and the shell method is that it depends on what we call a differential strip. So our differential strip here is these rectangles that comprise the area of our region here. Okay, so in a regular integral, a 2D integral, we're calculating the areas of these rectangles, right? And so we call these rectangles a differential strip. Okay, so we use the shell method when our differential strip is parallel to our axis of rotation. Okay, so if we were to rotate this around instead this way, we'll be using the disk method instead, because the rotation of axis, the axis of rotation is perpendicular to our differential strip. But here, since our rectangle is parallel to our axis of rotation, we're going to use the shell method, right? So going back to our illustration here, when we rotate these rectangles around the axis of rotation, we get cylinders. And when we add all those cylinders up, we approximate and we get a good glimpse of the volume of this solid, right? So what is the surface area of our cylinders here? Well, it's pi times the radius of the cylinder times the height of the cylinder. Okay? So now we have to think about what is our radius of our cylinder and what is the height of our cylinder. Okay? So the radius of our cylinder can be described as the y value of where it's at, right? So our radius of the cylinder can be described as our y value. Okay? So our radius, let's just write it here, is going to be y. And our height of our cylinder is going to be where this rectangle touches our graph, which is going to be 4y squared minus y cubed. Okay, so 4y squared minus y cubed. So our radius is going to be, I guess, the width of the rectangle in that sense, and the height is going to be our function 4y squared minus y cubed. Okay. And also I realized another thing. I switched up these axes. This should be x and this should be y. I should do this now, just not to confuse you guys. Okay. So this is actually x. And this is our y. Okay, cool. So now we know that the shell method calculates the areas, the surface areas of cylinders, and adds them all together. So we can now write out our integral here. So integral is going to be, our bounds are going to be y equals 4 and y equals 0, because that's where the region is bounded by. And our pi and our radius is y, and our height is 4y squared minus y cubed. Okay, and we're going to integrate in terms of y. Actually, I should put 2 pi here. I forgot 2 pi. Okay, so first of all, I'm going to zoom out a bit. So first, we're going to factor out our constant here. So it's 2 pi of 4, 0 of, I'm going to expand to 4y cubed minus y to the power of 4 dy. Okay, and now we're going to use our power rule of integration to integrate these two, this function here. So we have 4 over 4. So we have just y to the power of 4, and we have minus 1 over 5 y to the 5 of 4 and 0. Okay, so we're going to evaluate this definite integral now, which is 2 pi of 4 to the power of 4 minus 1 over 5 to the power of times 4 to the power of 5 minus 0 to the power of 4 minus whatever 0, so 0. Okay, so this is our definite integral. So we're going to calculate this, which is 2 pi times 256 minus 1024 over 5. Okay. And that's equal to 512 over 5 pi. Okay, so this is the volume of the solid that is created by revolving this region around the x-axis. Okay, and we use the shell method because we realized that our differential strip is parallel to our axis of rotation. Okay, so the solution that the junior tutor also provided is correct, so this solution is correct. Okay. Alright, let's move on to our last question of the day, which reads, what is the integral of sine x cos x? Okay. So we're going to use substitution here again to simplify our integral. So let's write it out first, sine x cos x. So we're going to let u to be equal to sine x. Okay. So now we know that du over dx equals to cos x, or du equals to cos x dx. Okay, so this is 1 and this is 2, and we're going to sub it in. So sub 1 and 2 in. So that gives us u equals sine x, so it's u, and cos x dx equals du. So wow, look at that. We found a very simple integral for us to solve, which is just integral of u du. And according to our power rule, that just equals to half u squared. We're going to sub back in our u here, which is sine of u, or sine of x, and we get half of sine squared x. Oh, don't forget the constant c. Okay, so that's how you can use substitution to simplify our integral. Okay, And this is also what the junior tutor did, and the solution is correct. Cool. All right, so this wraps up today's session. I covered 13 questions ranging from algebra to quadratic functions to derivatives, integrals, and I hope that you guys learned something today. And I wish you guys a good night. And if you guys have any other questions or any other need help with your mathematics, please submit them through OneClass and we'll try to get to them as soon as possible. Thank you so much for listening. And